on the bottom. So negative 2x equals 4 pi over 2 minus pi over 2. How many pi over 2's is that? 3 pi over 2. And then divide both sides by negative 2 again. Oh yeah. Oh yeah. Feeling it. A couple of years ago, we moved into our house, our new house, right? A couple of years ago, and the house we bought, they're like half-acre lots, so they're not, I mean, we're spread out a little bit, right? And all of a sudden, like after a week of living there, freaking like vibrations are rattling the pictures and stuff on our walls, right? I mean, like serious bass, serious bass, right? So I'm like, where the hell is this coming from? So I go, and it's coming from the neighborhood next to us, right? It's so loud, or not loud, but so like, you know, bassy, whatever that is. So it turns out, long story short, I drove over there because I want to see what the, you know, like what is this, right? So it turns out the guy that lives there, he's like in his 20s. He's like the Texas champion of bass for a vehicle, right? He's got like a Suburban full of freaking batteries and subwoofers and shit. And I'm just like, oh my God, you know? So I just had to talk with him. I was like, please, man, come on, you know? And finally, he wouldn't stop. He wouldn't stop. So winds up, he didn't live there, it was his parents. And so, long story short, he eventually stopped.
Just being an ass. Just being an ass.
I thought you were going to say you cut his power or something.
No, I didn't. I just, you know, it was a nuisance, but, you know, I don't want to be that party pooper, you know, but it was like, we're like a mile away almost, you know, it's like, and you're vibrating shit on my house. Like, what about your neighbors, you know, like some consideration, right? And so, yeah, and he was like in his late 20s. I was just like, come on, dude. All right, sorry. That's it, we got them all, right? All 4 points. Let's put these on. We have to be extremely careful right now. Extremely careful. This is the first time we've had this come up. I'm gonna leave that there. I'm gonna just try and stick this right in here. Let's look at where these points are. Where are the points? First one, when we set it equal to 0, we had what? Pi over 4. I'm just going to put that here. What's our next point? 0. Wait a minute. That's over here, right? Where's our next point? Negative pi over 4? Where's our next point? Negative pi over 2. That's here. And where's our last point? Negative 3 pi over 2. All right. You with me on this? We have to think about this in the order that those appear. This is a sine function, right? This is a sine function. So we know for all sine functions it's going to be the beginning point, middle point, end point, right? See, I think what do y'all understand what I'm doing? You might be tempted to say, oh, it's this sine curve like this, right? You might be tempted to do that. But think about the way these points appeared when we created them, right? At 0, it created this one, right? And then when we did the second equation, we got this point. The third equation, that point, fourth and fifth. So our sine curve is actually supposed to go this way. So does this sound confusing already? A little bit? Yes.
At the end, you have negative 3 pi over 2.
What is it? 3 pi over 4? Yes, I messed that up. Thank you. So look, this can get tricky. So what I recommend you do so that you don't make a mistake is just plug one of these values in. See, we're unsure. What we're unsure of is whether or not this thing goes up, you know, whether or not the sine curve goes up and down, or if it goes down and up. And I know that there's a flip over here, and maybe that will help us. But look, if we just plug one of these into here, we should know. So let's just plug 0 in. All right, so I'm curious, what happens at 0? Plug 0 in for x, what do you get?
pi over 2.
You just get pi over 2. Do you know what sine of pi over 2 is? You better. Sine of pi over 2? Pi over 2 is straight up, right? Sine of pi over 2 is 1, right? So this right here, if I plug 0 in, this right here gives me a 1. Yeah? But then times negative 1, which means it's down. So this point is actually down here. Now what was my amplitude? 1? So negative 1, here's positive 1. I have a point. I feel like I've lost some of you here. Got a point here. Yes?
Shouldn't the negative 1 be at 0?
Well, I haven't done my shift yet. I haven't done my shift. I'm going to. I'm just drawing this sine curve, and then I'm going to say, but remember, the whole thing's got to go up 1. I haven't done that yet, right? I'm just looking at this right now. So from that, what I can see is that it goes down and comes back up. This is going to be a high point on my graph. And then I can connect them, all right? Y'all still all right? Now, I'm going to start drawing my sine, but I'm going to do it dashed. And the reason I'm doing it dashed is because I have to remember now that this whole picture moves up 1. So every point that you see has to be shifted up 1 unit because of this. So let's move every point up 1. This point goes up 1, goes to here. 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 And so when I draw it, it now looks like this. See, that's much more complicated, right? There's a lot more going on there. On your homework, you will not have anything like this. Like, you won't have anything like that. That's what really causes the issue. And I believe you won't have any negatives here. You may have a shift up or down on the homework problems.
So what exactly made the line go from left to right to right to left?
The negative in front of the x. Because the negative in front of the x equates to having a reflection over the y-axis.
Okay.
So that's really where it's coming from. It can just get really kind of hard to keep track of the reflection, so that's why the 5 points are... You do the 5 points, you put the 3 you know are there, and then on the one these 2 you're unsure of, just test one of them, and that'll guarantee lock that point in for you. Does that make sense? Then you're not worried about reflections, you're not worried about, you know, oh, which way does it go? Does it go out to the left or to the right? Just lock in that 4th point and you're in business. All right. 20 minutes. Let's talk about tangent. So we're now into the next section, 7.7. 7.7. Oh, I have this to show you. I'll zoom in here in a moment. This is one of my old tests. There we go. So this was a test 1. I don't know why this problem appeared on their test 1, but look at number 17 and 18. Graph the sine function, graph the cosine function, right? That's exactly what we just did in class. So that's the type of question I would ask on a test. And then on exam 2, I believe in the very beginning, in the very beginning of exam 2, this is a review I had given another class, I asked them to graph the cosecant and secant functions, which we haven't talked about yet, right? We're going to do that, just not yet. All right, let's get to tangent, yeah? So this is 7.7. We're going to look at tangent, cotangent, secant, cosecant. We want to know what the graphs of these look like. Last class we talked about sine and cosine, and we talked about their properties. And we had said that for sine and cosine, there it is, this one. We said that the domain was everything, right? You can plug any angle you want into sine and cosine. The range was between -1 and 1 for the standard sine and cosine function, right? For the standard ones. If we shift them and stretch them, it's different. But for the basic sine and cosine, you can plug any number in, any angle, and you're always going to get numbers out between -1 and 1, right? So does that apply to tangent as well? Well, let's see. So let's look at y equals tan x, or tangent. Yeah, let's go tangent of, let's go tan x. And I'm going to go to my circle again. And let's just start out at 0. So if my angle is 0, what's tangent? What's tangent by definition? The y coordinate over the x. So this is 1, this is 0, right? So if I'm at 0 degrees, let me make a t-table over here. This is the angle I'm plugging in, this is tangent the angle. So at 0 degrees, or 0 radians, what do you get? 0 over 1, which is 0, right? All right, let's go to, I know we could go to pi over 6. Let's go to pi over 4 right here. That's root 2 over 2, root 2 over 2, right? So what would tangent of pi over 4 be? 1, right? That's root 2 over 2, the y coordinate divided by the x coordinate, and since they're the same, you get 1. All right, so if I'm trying to graph this function, here's what I have so far. At 0, this graph is 0, right? I'm trying to graph what this looks like. And I know that at pi over 4, if I plug that in, I get 1. So does it come back down? Does it look like sine? Does it look like cosine? Well, I don't know. Let's go to our next angle. Let's go straight up. What angle is that? Pi over 2. And what is tangent to pi over 2? Undefined, right? Because you have your y coordinate divided by 0. Y divided by x is undefined, right? This never happened with sine and cosine. It's happening with tangent, though. And so what we have at pi over 2 is undefined. So there's no graph there. We have no graph for tangent at pi over 2. So if I don't know what's happening at pi over 2, maybe I can take an angle that's really close to it. I want you to think carefully about that point right there. Think about that point. Okay, so I'm at an angle really close to pi over 2. Not quite at pi over 2, a little bit smaller than pi over 2. Tell me, is this x-coordinate big or small? Small. Small, because to be up there, I've got a really small x-coordinate, right? So this is a tiny little number that says tiny, tiny. It's so tiny you can barely read it. Tiny, right? That's a tiny number, right? Now, what about the y-coordinate? That's a bigger number, isn't it? This is a bigger number. Big number. Big number. All right? What happens when you take a y-coordinate divided by an x? What happens when you take a big number and divide it by a small number? It's positive, yes? But is it big or small? Take a big number divided by a small number. It's big, right? Think of a number. What if I take 10 and divide it by 0.02? That number is going to be bigger than 10. It's going to be a big number, right? That makes sense? And if I go a little bit closer, right, an angle a little bit closer, what happens? This number gets smaller, right? And this number gets bigger. So now I have a bigger number divided by an even smaller number. That should get even bigger. Make sense? So the closer I get to pi over 2, the bigger my answers are going to be. And so what you get is something that looks like this. You have what you call in college algebra a vertical asymptote. The closer you get to pi over 2, the larger the output of tangent becomes. If you don't believe me, get your calculator out, put it in degree mode, and try to put tangent of 90 degrees. And tell me what tangent of 90 is on your calculator. It should tell you something like, what? Tangent of 90? Make sure you're in degree mode. Tangent of 90? Error? Yeah, you should get an error because it's undefined, right? Pi over 2 is 90 degrees. Okay, how about tangent of 89 degrees? What's tangent of 89 degrees? $57? Wow, okay, that's a pretty big number, right? How about tangent of 89.9? 500 something? Okay, how about tangent of 89.99? 5,000? How about tangent of 89.999? Put like 5 or 6 nines there. Big, big numbers, right? They're starting to get bigger and bigger and bigger. That's the idea here, is that when we graph the tangent function, at 0 you're at 0, but as you get closer to pi over 2, you start to grow without bound. It starts to become infinitely large. Understand? Okay, so we have a problem there at pi over 2. So let's stop. Let's try and see if we can make our graph go backwards. So what would happen instead of being here? What if we went to this angle? Let's go to negative pi over 4. Can you tell me what the value of tangent is here? If I rotate negative pi over 4, what is it? Negative 1, right? Because it's still the y divided by the x. This is root 2 over 2. This is negative root 2 over 2. So if I take y and divide by x, I get a negative 1, right? So if I go here, this was 0. If I go backwards to negative pi over 4, I get negative 1. What about at negative pi over 2? What if I rotate down to here? That's 0, negative 1, isn't it? What's the y divided by x? Undefined again, right? So here at negative pi over 2, I have an issue again. Any guesses as to what's happening with this graph if I go closer and closer to negative pi over 2? Yeah, it's going to dive down. You could try it on your calculator. What would you type into your calculator to verify this? Tangent of what? What's an angle that's really close to negative pi over 2? Negative 89. What's tangent of negative 89? You're probably going to get negative 57. And you go negative 89.9, it's going to be even bigger, right? Negative. So you get this. Huh. Okay? So this is what the tangent function is doing between negative pi over 2 and pi over 2. Here's what it looks like. It's a weird function, right? It's not like the sine function. We don't have a domain of everything, right? We can't plug anything we want into tangent. We have to be very careful what we plug into tangent. And the range is no longer between negative 1 and 1. It's between negative infinity and infinity, right? So a very different type of function. Now, if we continue this graph, once we get past 90 degrees, let's say we go here. What's that angle right here? 3 pi over 4. So if I were to continue here, what would happen at 3 pi over 4? Do it on your calculator. What do you get if you do tangent of 3 pi over 4? Well, yeah, I mean, you don't need your calculator for it. Tangent at here, we should have a negative 1, right? Because the x-coordinate's negative, y is positive. So we should be here. What about at pi? What's tangent of pi? Negative 1, 0 is the coordinate, right? Take the y, divide by x, you get 0, right? So at pi, you should be 0. I'm running out of room. Where would we have the next problem? Where would our next issue of division by 0 come in for tangent? We had it at pi over 2, didn't we? Where's the next place we're going to have a problem? 3 pi over 2. So over here at 3 pi over 2, we have another vertical asymptote. And you know what? I have pi. I need a 5 pi over 4 in here. That's a terrible picture now. Goes like this. I need to erase that. My spacing isn't right there. There. Here, here. This is 3 pi over 2. This is 5 pi over 4. Goes up and goes forever like that. And guess what? It keeps doing the same thing. If we keep going, it's going to do that picture again, and then again, and then again, with vertical asymptotes spaced out along the x-axis as we go in both directions. Y'all okay?
So is a cubic graph just a tangent?
Oh, good question. A cubic graph is not a tangent because if you look at like the function f of x equals x cubed, it looks kind of like a tangent function because it does do this. The difference is that this graph, as you move to the right, it continues to go up. You never have a vertical asymptote. You never have a barrier. See, this is a barrier. So it goes up and up forever, but it never goes past to the right, and you never go past pi over 2. Where on this graph, you know, pi over 2 is here somewhere. You go right through it, right? You see? So the shape kind of looks the same, but it's not. I guess another way I could demonstrate is like if I draw a parabola, right? The implication here of a parabola is that these keep going out forever. That's different than a graph where I would have vertical asymptote here, and I have something that goes in like that. See, I'm stuck between these two walls. I can't go out past them. Here, I go and I flare out. Make sense? So that's how they're different. I mean, there's other things that are different, but that's the main difference. So let me see. For this tangent function, this is going to be a tricky one. I want to know for y equals tan x, see if anyone can figure this out. I want to know the domain, and I want to know the range. Let's start with range because the range is the easier one. When you look at a tangent function, what possible outputs can come out? We said this already. Negative infinity to positive infinity, right? So the range, you can have any number come out of tangent. Right? You were doing it. You were doing tangent 89.9999, and those numbers were getting bigger and bigger and bigger and bigger. Right? You could do that for the rest of your life, 89.99999, and you would have it just get bigger and bigger. But the big question is, what's the domain? What can you plug in? Pardon? The U? Union? Is that what okay, yes. So one thing we could do is we could say, hey, look, the domain is everything between here and here, right? Everything between here and here, not including these 2 points, right? And then everything between here and here, not including that point and that point, right? And we could use unions, couldn't we? That's one way to do it. The other way to do it, which I think is easier, is to just tell me what it can't be. Instead of telling me what you can plug in, tell me what you can't plug in. Make sense? How many things can we not plug in? Negative pi over 2, right? Can't plug that in. Can't plug in pi over 2. Can't plug in 3 pi over 2. Can't plug in infinitely many things, right? But we learned a class or two ago how to represent an infinite number of answers, didn't we? So let's see if we can do that. When I'm talking about domain here, think about tangent. Freaking unit circle, right? Like if you understand this thing, it makes life easier Where is tangent undefined on this unit circle? Where? Physically, where on the circle?
Along the y-axis.
At the top and at the bottom, right? At the top and bottom. These are the 2 points where tangent is undefined. Why? Because in both these points, you have x is 0, and that's going to give you the division by 0, right? Right? So these are the 2 points. How can I represent these 2 points as a set of answers, all possible angles? So do y'all remember how I could do it? Start here. What's that angle? What's that angle? Let's go pi over 2. Let's not do degrees. So I'm saying here for the domain, x cannot be, right, pi over 2. And then how could you give me all the other points here, here? How do I get from here to that one? Add a what? Yeah, add a pi, right? And I get back to that one, add a pi. Remember the symmetry we talked about? They're directly across from one another. So I would say, as long as x is not at pi over 2 plus, you said it what? Pi k or k pi. It doesn't matter where you put the k. That's the domain. Pi over 2 plus any half rotation or any remember, k can be negative also. So this means either start at pi over 2 and either add or subtract from this any number of half rotations you want. All those numbers, take them out. They are not allowed in the function. That's your domain. So I think you would agree we have some more things that we have to worry about with tangent than we do with sine and cosine in terms of domain, right? All right. Let's see if we can't, in the last 4 minutes, see if we can't squeeze in cotangent. I think we might be able to. What would cotangent look like? Well, cotangent x, what's the only difference between tangent and cotangent? Reciprocal. So instead of y over x, it's x over y, right? It's x over y. So where will we have problems with cotangent? Where are we going to have issues when it comes to cotangent? If this turns out to be the x coordinate over the y coordinate, right? We're going to have problems where? At wherever the y coordinate is 0, right? So these are the 2 points where we're going to have issues on cotangent, because this is going to be 1, 0. That's our y coordinate 0, and here is negative 1, 0. So these are problems. So the domain for us is, for this, is what? X cannot be what? You can't be here, right? Can't be there. Can't be there. Can't be here. Can't be there. Can't be there. How do you say that?
2 pi plus pi k.
You could say 2 pi plus what?
Pi k.
Pi k. That would work. That's not the only answer. We could also just say, start here, right? And just start adding pi k's. What's here? You said 2 pi, but could I say 0? That's 0, right? Plus pi k. Half rotation. So you could do that, or if you don't like that, or you could say something like just pi k itself, right? You could also do pi plus pi k if you want to just drive yourself crazy, right? You could say, hey, let's start at pi and then just start adding half rotations. Doesn't matter where you start. You can add or subtract an infinite number of half rotations. I personally would go with this one, but they're all equivalent. So there's where we can't plug those in, right? Can't plug in any multiple of pi. And what about range?
All real numbers.
It should be similar to what happened with tangent, right? We're going to have these ratios. They're going to get really big, really small. So negative infinity to infinity. And so the graph of this will look like this. Where do we have problems? When x is, like 0, right? Pi, 2 pi. So I have a problem at 0, pi, 2 pi. At all of these multiples of pi, I have vertical asymptotes, right? That's a little different than tangent already, isn't it? Tangent had the problems at pi over 2, negative pi over 2. Here, 0 to pi. What happens halfway in here, pi over 2? What's the value of this function? At pi over 2, what do you get? 0. Why? At 0, what's the x divided by y? 0 divided by 1, that's 0, right? So we have 0 here. And because I'm out of time, all right, I'm just going to draw the rest. You could pick some points and check. It looks almost like the tangent, but it's opposite. This side goes up, and this side goes down. And then it continues that. Halfway between here and here, goes up, comes down. Goes up, comes down. Goes up, goes down. Just like that. Okay, so what I would like for you to do for homework is focus all of your attention on the 7.6, all right? We haven't done enough for 7.7 yet. Make sure you get all the 7.6 done. And we'll come back and we'll finish up next class. Looks like we're probably going to get through 7, yeah, for sure 7. We'll see how much 7-8 we get through. But be here next time because we're going to talk about the test. All right, y'all have a good day. Excuse me.